Hi everyone, this is the third video on gravitational fields for A-level physics. This video explains the concept of gravitational potential, which is difficult, and the calculations that go along with it. We will also look at equipotential surfaces and the calculations for mutual orbits. If you want to get the free PDF presentation and question sheet for this topic, along with lots of other resources, click on the link in the description below. Enjoy the video. So we come to the thorny issue of gravitational potential given the symbol V. Now this is an area of gravitational fields that a lot of students really struggle with, and to be perfectly honest, this is one of the areas which I find difficult to teach because it's quite a slippery idea in terms of the definition, in terms of the calculation, in terms of what it means. So it's definitely something which it requires a bit of thought. Now do check with your specification. I think most exam boards do expect you to understand this to some level, but there might be slight variations. So we're going to talk about, first of all, the definition. And then we'll try to piece all of this together and we will look at some calculations on the next slide. So first of all, the definition, it's the amount of work done by the field, that's important, per unit mass, on the mass as it moves from that point to infinity. Okay, right, so what have we got here? We've got our object, let's say in a low orbit position, so it has some gravitational potential energy. And if we then compare that to a situation where it is very, very far away, and we call that infinity, but we just mean deep space. So we mean the effects of the gravitational field are negligible. So at this position, the gravitational potential is zero, and the GPE is zero. Now this is quite an odd idea because we think, well, how can it be zero? Because if you imagine we are totally outside of the effect of the Earth's, in this case, the Earth's gravitational field, then we cannot have any gravitational potential energy or gravitational potential. So generally we're talking about the change in gravitational potential energy. So the gravitational potential actually increases from a negative value when we're somewhere in the field to zero when we are at an infinite distance. Right, so that's our definition, and let's look at the next stage. We've got V, which is not a very helpful symbol because normally we associate V with electric potential or potential difference, and there are similarities as we will see. But normally we'd write this as capital V and then with G or grav. So gravitational potential is minus Gm over R. Okay, so it looks very similar to our expression for little g, but that was divided by R squared. Now we could derive where this comes from, and we'll look at that later on. But the key thing to realize here is it's not an inverse square relationship, it's inverse proportional. So gravitational potential is inversely proportional to distance. Right, so let's imagine how we would draw this on a graph. So we've got V on the y-axis, we've got distance on the x-axis. Okay, so this negative sign is quite important here. And in fact, in the calculations, we will include this value because we have a negative potential when we are close, let's say when we're at the Earth's surface, RE, and that will get less and less negative, and it will approach zero, and this will be asymptotic as well. So that negative sign is important, and the relationship here is inverse proportional rather than an inverse squared. Right, so let's go back to the definition. So it's the amount of work done by the field. Well, the field isn't doing any work here. It's not attracting. If we were going the other way, if we were going from infinity to near to the Earth's surface, then the field would be attracting the object and doing the work. But we have to put the work in. This requires energy input when we're moving to infinity. And this is why it's a negative value. So the energy is input, and it's a little bit odd. Now there are other definitions. Sometimes you could define this as the amount of work done by the object or energy input. But certainly WJEC defines this by the field. Right, so again, let's look at this in some other ways. So if we compare this to gravitational potential energy, which is related but not the same, that is the energy an object has due to its position in a gravitational field. But this is the energy per unit mass. So we've actually, this gives us the units of joules per kilogram. We've also talked previously about electric potential, which is the energy per unit charge. So that is given the symbol V. That's E over Q, whereas we have E over M. So why is this useful? Okay, so if we wanted to work out the energy or the work done, or indeed the change in potential energy, all of which are the same things, if we can work out the change in gravitational potential, that's delta V or delta Vg, if we multiply that by the mass, that will give us the gravitational potential energy or the change in gravitational potential energy. Right, so this is very abstract, very difficult. I think the best way to put all of this into context is with a calculation, and we'll do that in a few minutes' time. Just before we move on from this screen, something to consider, and very often this comes up in the as an exam question, is if you're given or shown in the exam a graph of V against R, you may be asked to calculate the field strength. And what you'll need to do is to find the slope. So what you could do is draw a tangent at the point where we're told the radius, and then work out the gradient at that point. The gradient is the y divided by r, which is v over r. V we know is gm over r. If we divide by r again, that gives us gm over r squared, which we've already defined or derived in an earlier video as gravitational field strength. So that's, if you can understand the derivation of this, that's brilliant. Or you can just remember that the slope, the gradient at a point of a potential distance graph represents the gravitational field strength. Just before we move on to a practice worked example, I'm going to mention equipotential surfaces. Again, just check with your exam board whether you need to know about this. Certainly WJEC do include this. This is actually, even though it looks or it sounds quite complicated, this is actually relatively straightforward. So the definition, and you might be asked to write this in the exam, is an imaginary surface. So it's a surface because obviously we've drawn this as a two-dimensional drawing, but this represents a three-dimensional space. So it's the surface, it's not a physical surface, it's an imaginary surface of the sphere on which all points are at the same potential. Now that shouldn't surprise us, because if I work out the potential of my object here, let's say this is a satellite, or it could be the moon, that depends on the mass of the Earth and the distance between the center of masses. So if I move it over here, it'll have the same potential. In fact, anywhere on this circle, on this equipotential surface, it will have the same potential. But if I move further away, or indeed closer, then the potential will change. But anywhere on this circle, 2D, or surface of a sphere, 3D, the potential will be the same. And typically, you might get given a drawing where you're given values, and you have to work out the difference or identify that they're the same because they're on the same curve, the same equipotential surface. So the questions related to this tend to be quite straightforward. So let's look at a worked example. So find the gravitational potential. So the most important thing here is to use the right formula. We're so used to gravitational potential energy that a lot of students just get confused between that and what we're trying to find. So we're not trying to find for part A, the gravitational potential energy, we want the gravitational potential. So it's this formula here, and we will include the negative because by definition, that is important. But once we have the right formula, then the calculation should be straightforward, as long as we take into account that the height is above the Earth's surface, so we need to add that onto the radius. So we've got the right formula, hopefully. Big G, we know that. The mass, there's only one mass, that's the mass of the Earth. And we're going to divide by R. Be careful, it's not R squared, it's just R. Very, very common mistake. And we need to add together the radius and the height in meters, so this is times by 1,000, and we're going to get this value here. So expect a large value, and the units are joules per kilogram, as we've mentioned already. The work done per unit mass, so the energy per unit mass. And you would expect to include the negative sign because by definition, this is a negative value. That on its own, I think, doesn't really mean that much to us because we're not used to thinking about joules per kilogram. But part B hopefully puts this into context. So we're told the gravitational potential at the Earth's surface is this value here. So we would expect that to be larger than at the height of the satellite because we're moving away from infinity, we're getting a larger negative value. So we're trying to find the change in potential energy as we move between these two positions. So all we need to do is to work out the difference between these two potentials. Now, we could take into account the negative values here. So it would be minus 5.5 minus 6.27, and they're both 10 to the 7. For simplicity, again, we could just disregard the negative value and just work out the difference between the two positive values, so the magnitude of the difference. So either way we do it, it is the difference. So 6.27 take away 5.5, 10 to the 7, then multiplied by the mass. So this expression here, we're probably given that in the formula booklet, but if we're not, then we know by definition the potential is the work done per unit mass. So if we want the work done, or the energy, or in this case the potential energy, it's going to be the change in potential multiplied by the mass, and it's the mass of the satellite, not the mass of the Earth. And we would expect to get a really large value, as in this case, because we're moving a very large mass between the Earth's surface and its orbital position. So this is in effect the amount of energy required to put this object in orbit. Now in reality it's a bit more complicated than that, but this is the difference in potential energy. This is the final thing we will consider in gravitational fields, mutual orbits. Do check with your specification whether this is included. It is included in WJEC. Even if it's not included in your specification, it might well be worth having a look at it, because it's the kind of thing maybe for an AA star question, they could just say, here is something that you haven't considered that's not on the specification and you have to deal with it. So this may be on your spec or it may be a stretch and challenge, but I do think it's worth considering. Okay, what is a mutual orbit? Well, we could talk about binary star systems, but basically wherever you have an object orbiting something else, whether it's the moon around a planet, or a satellite around a planet, or a planet around a star, then we have a mutual orbit. Because normally we assume that the large object in the middle isn't moving, but it does actually move a little bit. And they have a combined center of mass. And normally the center of mass will be within the larger mass. And that's what defines a planet. So if we think about Pluto, which very sadly is no longer considered to be a planet, there are various reasons for that, but one of the reasons is this center of mass between its moon Charon and Pluto is outside of Pluto. So the moon is actually pretty big compared to Pluto itself. So we actually get quite a noticeable mutual orbit. So Pluto will be orbiting a common point. Generally speaking, when we're looking at stars, then this wobble is very insignificant. However, it's really useful, and we might look at this later on in the course when we talk about stars and the universe. So star wobble is something that we can look at through telescopes, and we can use that information to identify the number and the size and the distance of the planets orbiting that star. So this is very much a useful thing in astronomy. So what can we say about these mutual orbits? So as we know already with gravitational force of attraction, these forces will be equal and opposite, Newton's third law. It should be fairly intuitive that the larger mass will have the smaller orbit and will move more slowly because it's got a larger mass, but they both have the same time period. That's really important. Right, we have various formulae here which we need to consider. We're not expected to derive these, fortunately. You can look into that if you want to, but we're not going to do that in this video. So we've got, before we look at the formula, let's identify what all these symbols mean. So we have M1, which I've called the smaller mass with a larger radius, and M2 is the larger mass with a smaller radius. R2 is associated with M2, and R1 is associated with M1. So we have a center of mass. So this case here could be Pluto and its moon, or it could be a binary star system, where both of these objects are orbiting a common center of mass, which is outside of the larger mass object. D is the distance between the two centres. So if we have a look at this one here, we've got R1 is equal to M2 over M1 plus M2 multiplied by D. R2 is the same idea, but we've kind of swapped these values over. D is still on the top, but now M1 is on the top, but the total mass M2 plus M1 is on the bottom. And then the time period, which will be the same for both of these masses, is given by this expression here. You should see a similarity here with Kepler's third law. Obviously it's different, but there is a relationship between Kepler's third law. So let's have a look at a calculation, and hopefully that will give you a better understanding. So we're going to look at Pluto and its moon. So we're going to find the orbital radius first of all, and then we're going to calculate the orbital time period. So we're given big G, we're given the mass of Charon and Pluto, and the separation. Remember, that's between the two centres of mass. So first of all, we could call Pluto M1 or M2. In this case, I've called that M1. So we're going to find R1. So we're going to have M2. So it's the other mass, it's the smaller mass, it's the mass of Charon, which should make sense because the radius should be larger. So we'd expect to have the smaller mass on the top. We're going to multiply, we're going to leave this in kilometres, so multiplied by D, 19,600, divided by the total mass, and we get our value here, 2,120. And then if we're trying to find the mass of, the orbital radius of the moon, it's going to be, we could do the same calculation but with the other formula, that's absolutely fine, but it's probably easier because we know the total distance and we know the radius of 1, and the total distance is the sum of the two radii. Probably easier just to subtract our previous value from D. So 19,600, take away our first answer, and we get 17,500. So that should make sense because R2 would be larger because that's further out, that's the smaller mass. Okay, so if you want to check, you could use this other formula here, but you should get the same value. And then part C, or part B rather, we're trying to find the orbital time period. So this should be a straightforward substitution. So 2 pi is on its own. We're going to find the square root of D cubed. Remember, this is kilometres. So we're going to have this in meters. So 19,600 multiplied by 1,000, and then all cubed, then divided by G, and we just add together the two masses, and we get our answer in seconds. So depending, that's probably fine for this question, but we might be asked to write that in hours or days, so we can convert that as required. Well done. So we have now completed the gravitational field lessons. So this is the end of the third lesson. If you haven't already looked at the circular motion videos on YouTube, I recommend you have a look at those. You can also have a look at all the first year topics for Physics A-Level, and the second year topics will be coming soon. If you want more detailed support with your Physics A-Level, then go to payhit.com, Grade A Physics, and there's loads and loads of stuff there which will be really useful to improve your grade and to push it up to the highest grade you can possibly get. Thanks for listening. See you next time.